All right, welcome back everyone. This should be the first video in week 8. And to start off week 8, I'm going to talk about the difference between a conservative and a non-conservative force, all right, and how that relates to its energy, all right. So you saw in chapter 7, the previous chapter, the relationship between a force that does work on an object as it moves across a distance, right, or through a distance, and how that related to the object's change in kinetic energy, right? One half or delta, one half times the mass times the change in speed squared, okay? Work equals delta K, in other words. Chapter 8, right? This chapter deals more with the overarching concept of conservation of energy, okay? And we'll see that in later videos. But in order to do that, we need to talk about the difference between these two types of forces, right? So, conservative forces are a type of force, not a type of force like the normal force or friction or gravity, right? Those are specific forces. But for lack of a better term, conservative forces are an entire branch of certain kinds of forces. Let me explain more with numbers here. Okay, so assume, for example, we want to pick up a box, right? Or this very lopsided, actually, let me just do it over here. Okay, if I were to write or draw some box, and then if we were to pick it up, right? Let's say we put our hand underneath here, right? And then we pick it up, we force it up. So we apply a force upwards. So we apply some force F, okay? And that's at some magnitude, right? Whatever it is. As the box moves from some, we'll say, initial height, which I'll call y1, up to some final height up here, y2. As that moves up, right, through some distance d, or displacement, if you will, that applied force does some work on it, right? It does a positive work because that applied force is in the same direction as the displacement, okay? Right? F dot d or F dot dr, right? Now, as the box is moving from the initial height to the final height up here, there's also another force acting on it, right? What's that other force? Well, the gravitational force. So Fg. And remember, that's equal to mg in magnitude. And in this case, if I specify up to be positive, it's in the negative direction, okay? So now, as you pick up this box from the initial height to the final height, let's calculate the work done by that applied force F, okay? So it's equal to, well, the integral of that force dotted with the displacement. Yes, it's dr, right? But really, it's just in one direction. So that dr can really be trimmed down to just a displacement in the y direction, right? They're both in the same direction. So it's whatever the magnitude of the force is times the magnitude of the displacement, right? If we integrate over dy, we effectively add up all of these tiny displacements such that overall we get d. So now it's just F times d, and then it's cosine of 0, since 0 is the angle in between. All right, distance now. Since 0 is the angle in between F and the displacement, right? And so the work here is positive FD. Whatever that number is, right, it's positive. Let's calculate the work done by the gravitational force as we pick this box up from a starting height here to a final height here. So again, it's integral F, in this case it's the force of gravity, dot dy. And now Newton's third law tells you that the magnitude of the gravitational force should be the same as the applied force in this case, right? Let's go further and say there is no acceleration. So now those forces have to be equal. The magnitude of gravity is mg, all right? And again, if we integrate dy, we get the total displacement, in this case d, and cosine of the angle in between these, well, gravity is pointing down, but the displacement is going up. So that is an angle of 180. And so this gives us an overall work that's negative mgd. And because of Newton's third law, we can go up here and say the work done by the applied force, right, our hand, in other words, is the same. So mgd. Okay? So if you add up all of the forces doing work on an object from some initial point to some final point, add up this plus this, what do you get? Well, you get 0, right? It doesn't matter what these actual numbers are. In this case, right, there'll always be mass times gravity times the distance traveled. And over here, mass times gravity times the distance traveled. And again, that comes straightforwardly from the force dotted with the displacement. Okay? So whatever the mass of that object is, whatever planet we're doing this experiment on, the value of gravity doesn't really matter. And regardless of the height that it's changing, right? These two forces will always be on an object. And so the total work going from some initial to final position will be 0. We can do the exact same thing, and now we'll start up here and then we'll go down to where we started, right? We'll effectively reverse this problem. When you do that, you should get the exact opposite. So we'll call it up, right? Part up, and then we'll call this next part down. So the work done by the applied force, now it's moving down. So let me take that away. The displacement now is moving down from y2 down to y1. Let's actually put that in there. Okay, let's evaluate this now. Well, the magnitude of the force, now that we know, is mg. Integral of dy. Well, that's, again, just the total distance traveled, right? But now we're going down from y2 down to y1. Okay, so this again is d, and the angle in between the applied force, which is still up, and the displacement now is down, is 180, right? You can think of this as your hand still being on the bottom of this object, but you're just lowering your hand, right? You're bringing this box down towards the ground. So you're still applying a force upwards, right, against gravity, but you're just lowering it. Yeah. So now it's cosine of 180. And so in this case, it's negative mg d for the work done. And for the work done by gravity, can you see what's going to happen? Right? Evaluating the magnitude, mg, the integral of dy gives us a distance of d, and now force of gravity is now parallel to the displacement. So this is cosine of 0, which gives us a positive mgd. Aha! So again, from some initial point to some final point, the total work done in that process is 0. However, this is the important part of this video, right? Just looking at one of these forces, when we start at one point, go up to another point, right? And then back down to that starting point, that complete cycle, excuse me, the work done by one of these forces is, well, plus mg plus negative mg. So for that entire process, the total work done by the force F is 0. Similarly, the total force or the total work done by the gravitational force in this process from y1 up to y2 and back down to y1 is negative mgd plus positive mgd. So again, it's 0. And this is the crux of what a conservative force is, right? In that the work done by a conservative force does not depend on the path taken. It only depends on the endpoints. It only depends on where you start and where you stop. Okay? So, for example, a conservative force in this case would be the gravitational force. Because I didn't mention it, but we could have started here at y1 and went like this, looped around, right, taking our time, and then ended up boop at y2 sometime later. And because the normal force doesn't depend on distance, it just depends on the overall change in distance, right? The dy, which is just d. We will always get the same total work done, right? So you can start here and go straight up, or you can start here and go looped around and take your time and then end up at y2. You'll do the same work. So in summary, for conservative forces, they are independent of the path taken, right, between the two start and end points, right? There is 0 net work, in other words, 0 total work done around a closed path. And in this case, the closed path was starting at y1, going up to y2, and back down to y1, right? That's a closed path or a closed loop. And thirdly, for conservative forces, the potential energy depends only on the position, okay? Only on the position. That's why in the last chapter, we saw the potential energy be mgh. In this case, my h is d, so mgd. Okay? And two examples are the gravitational force and the elastic spring force. For non-conservative forces, this previous example does not hold. The work done by a non-conservative force depends on the path taken, right? In other words, the energy expelled by a non-conservative force depends on how far or how long that force acts on it. For example, kinetic friction. If you push a block across a floor, right, if it starts there and ends, say, here, right, that's some distance we'll call d, and it gives off some energy due to friction, right? It loses or it heats up because it loses energy because of kinetic friction between the floor and the box. However, it's going to lose more energy if it goes even further, say to 2D, right? So that amount of work done depends on the path taken. Another example is air resistance, okay? So these are two overarching general types of forces. Don't think of conservative or non-conservative forces in the same vein as a gravity, as a tension, as a spring force, right? Those are, I guess, specific forces from specific mechanisms. Sorry. Conservative forces are kind of an overarching general type. Okay. Well, with that, in future videos for this chapter, I will have examples showing the difference between conservative and non-conservative forces and their relationship to conservation of energy, right? So please watch those. Well, that's all for this video. Thanks for watching.